Under the special topics playlist, let's talk about the Levenberg-Marquardt algorithm for training artificial neural networks. Of course, if you look at the Levenberg-Marquardt algorithm, of course, that's some kind of optimization uh, algorithm. But then we have that uh, in conjunction with artificial neural networks. And if you follow my playlist on the mathematics of artificial intelligence, you'll discover that the most popular algorithm we use there is the gradient descent algorithm. But let's see the difference like Levenberg-Marquardt algorithm makes. So, the learning objectives, by the end of this lesson, you should be able to explain why training an artificial neural network can be formulated as a nonlinear least squares problem, derive the Gauss-Newton algorithm from a first-order approximation of the residual vector. So, the idea of residual vector is very key here. Explain the motivation for the Levenberg-Marquardt modification, derive the Levenberg-Marquardt update equation, construct the Jacobian matrix of neural network residuals with respect to network parameters, understand the role of the damping parameter. So there's a damping parameter that comes up in the Levenberg-Marquardt algorithm, which going forward, I might call it LM algorithm. Then explain how Levenberg-Marquardt behaves between gradient descent and Gauss-Newton, right? So implement a simple neural network trained using the Levenberg-Marquardt algorithm in Python, and then compare Levenberg-Marquardt with gradient descent and standard backpropagation. Then identify when Levenberg-Marquardt is appropriate and when it becomes impractical. So these are our objectives. Now let's start by looking at why the Levenberg-Marquardt algorithm may be necessary. Artificial neural networks are commonly trained using gradient-based optimization methods such as gradient descent, which is about the most popular. Sometimes talk about the stochastic gradient descent. Then you have momentum methods, Adam and RMS prop. However, these methods are not the only possibilities. The LM algorithm provides a powerful alternative for neural networks whose training objective can be expressed as the sum of squared errors. So we've come across that a lot, especially if you follow the mathematics of artificial intelligence playlist. So the key idea is to combine two optimization philosophies here. So we combine gradient descent, which is relatively stable but can be slow, and Gauss-Newton optimization, which can converge much faster near a solution. But of course, that would most likely require more compute power. So the Levenberg-Marquardt algorithm introduces a damping parameter that allows it to move between these two behaviors. So Levenberg-Marquardt algorithm or LM algorithm is something between gradient descent and the Gauss-Newton optimization, and it does that with the help of a damping parameter. This makes LM especially useful for small and medium-sized neural networks and nonlinear regression problems. So if it is not small or medium-sized, LM may not work. That's necessarily what we are talking about here. Now, let's look at neural network training as an optimization problem. So consider a neural network with a parameter vector theta, which has p parameters from theta 1 to theta p. So the parameters include all weights and biases in the network. Of course, if you have not seen the mathematics for artificial intelligence playlist, you want to check the first video, where I got to talk about the 5 equations powering artificial intelligence. Then you're going to see the idea of the of weighted sum in or linear transformation. So there you talk about weights and biases. Now, for a training observation I, let yi be the observed target and yi cap of theta be the neural network prediction. So the prediction error or residual is the difference between the observation and the target. So r sub I of theta will then be y sub I minus y sub I cap of theta. So for n observations, we then define the residual vector across. So we have r theta from r1 all the way down to rn of theta. So the sum of squared errors objective will then be e of theta, which is half of summation from I equals 1 to n of ri of theta all squared. That's this difference now. So it's more or less like the mean squared error we've always talked about under artificial intelligence. So in vector notation, we can say e of theta then is half r of theta transpose r of theta, like that. So therefore, training the neural network becomes a nonlinear least squares optimization problem. It is nonlinear because of the square you have here, and this is nonlinear because you are multiplying two matrices like that. So Now, another question is, why is neural network training non-linear? Now, suppose a neural network contains a hidden neuron with sigmoid activation H equals theta of Z. In fact, if you still check the very first video on the Mathematics of Artificial Intelligence playlist on my channel, you see we talk about activation function, the sigmoid, and yeah, there are different activation functions, including the sigmoid function and the ReLU function and co. So where here now Z is Wx plus B, which is simply a linear transformation where W talks about the weights and B talk about the biases. And then we now have sigma of Z to be 1 over 1 plus e raised by minus Z, which is a sigmoid function. So the derivative of the sigmoid function is actually sigma of Z, which is sigma of Z into 1 minus sigma of Z. I think in one of the videos under that playlist, I actually went ahead to see how we derive this. So all you just need is differentiate this, and you discover that at the end of the day, that derivative is equal to sigma of Z multiplied by 1 minus sigma of Z. And by the way, sigma of Z is always between from 0 to 1. And that's why we can express it this way. Now, suppose the output Y cap is actually VH plus C. That's the output. Then we can say Y cap is equal to V sigma of WX plus B plus C. So the parameters W, B, V, and C occur inside. So these parameters W, B, V, and C actually get to occur inside nonlinear functions. Consequently, we say that Y cap is equal to Y cap of theta, and that is not, and we say it is nonlinear in the parameter vector. So therefore, neural network training is generally a nonlinear optimization problem like that. And then we talk about the residual perspective. Now, before now, we already derived the idea of residual. The residual is simply the difference between the target and the predicted value, between the observed value and the predicted value, if you like. So the Levenberg-Marquardt is most naturally understood through residuals. For each training example, you say Ri of theta, R sub I of theta equals Y sub I minus Y sub I cap of theta. And the training objective is E of theta, that's the loss, right? E of theta is equal to half square root from I equals 1 to n of R sub I squared. So the important point is that Levenberg-Marquardt does not directly approximate the entire neural network loss function. Instead, it locally approximate the residual functions. And this distinction leads naturally to the Jacobian matrix. Now, talking about the Jacobian matrix, right? Let the neural network have p-trainable parameters from so that you have the residuals R of theta to be from R1 of theta all the way down to Rn of theta. Then the Jacobian of the residual vector can then be seen to be J equals partial R partial theta. So, you have theta 1, all the theta 1, theta 2, whatever number of parameters you have. So you have J equals the partial R partial theta such that we can have the Jacobian. J is the R1, the theta, partial R1 over partial theta 1, partial R1 over partial theta 2, all the way down to theta P. And then we do partial R2 over theta, partial theta 1, and so on. And then up to partial Rn, partial theta 1, all the way to partial Rn, partial theta P. So here we have P parameters, and then we have N residuals like that. So here we have does the Jacobian matrix has dimensions n by p. That's n residuals, each having p parameters. So each now describes how one residual changes with respect to all network parameters, and each row here describes how one residual changes with respect to all network parameters, and each column describes how one network parameter influences all residuals. So then we have a simple nonlinear model. Consider that Y cap is equal to WX squared plus B. Suppose we have observations x1, x1, y1, x2, y2, x3, y3. Then the residual will have to be Ri equals yi minus wxi squared minus b, based on what we have here. So that is the residual now is simply this Y cap now minus wx squared minus b. So that gives us the residual because that's what we have. So the parameters then will be theta. So the parameters are theta, WB, like that, the weights and the biases. Therefore, we can have the Ri, the W. So that's the R1, the W, the R2, the W, all the way to the last one. And all of that now, if you differentiate this expression with respect to W, you get to have W goes and you just have minus xi squared. There's no W here and here, so they go to zero. So the RIDW is minus xi squared because they are the parameters, they are the weights and the biases, W and B. Then you also have, so this is the gradient of the residuals with respect to the weights, and then with respect to the parameter to the with respect to the biases, now you have this minus b here. If you differentiate minus b, you just get minus one. Hence, we can say that this simple example illustrates exactly the same mathematical structure used by the Levenberg-Marquardt for neural networks. So in this case now, for the first one, the RIDW, you have minus xi squared. That means that for the first residual, you have minus x1 squared. Second residual, you have minus x2 squared. Third residual, you have minus x3 squared. And then for the biases, you just have minus one all the way through. So had it been that minus b has an attachment, it has something else attached to it, would have also been able to vary it for all the residuals. So that goes. So we see that that's a simple nonlinear model right there. Now let's talk about gradient of the least squares objective. Recall that the expected value of theta, so to speak, is actually E of theta is actually half R transpose R. That is the transpose of the residual multiplied by the residual. Now, if we use chain rule, we then have that the grad of E is actually the Jacobian, right? The transpose of the Jacobian multiplied by R, like that. Thus, we can say that is this grad or delta? I think grad E also is now J transpose R up to the sign convention used for defining the residual. So if we then define E to be Y cap minus Y, then the gradient acquires the corresponding sign also. So the important structural result is that the gradient is obtained from the Jacobian and residual vector. So we have the residual and then the Jacobian comes out of it along the line. So the important structural result is that the gradient is obtained from the Jacobian and residual vector. Now, from Newton's method to Gauss-Newton. Now, we have established it when we started the whole idea of the Levenberg-Marquardt algorithm, that is, its behavior is somewhere in between the gradient descent method and Gauss-Newton method. So, but let's see how the progression from Newton's method all the way to the Gaussian-Newton method. By the way, the Newton method is in one dimensional form, right? The Newton method is actually it converges very fast, and it is that case where you have something like xn plus 1 being equal to xn minus f prime. Is it the derivative that is at the top now? I'm trying to remember. I think it's f prime. Okay, I think it should be f of xn at the top. I think f of x sub n all over f prime of xn. I believe this is it. The confusion I have is maybe the prime is up. I think the prime is down because I remember, if for a function that cannot be differentiated or whose derivative does not exist, this I think it should be at the top. I'm not very sure. I guess it should be at the top. So we have f prime up here and this one is down here. But if that is not correct, we'll definitely see that along the line. Yeah, I think so. Because this is the Hessian now. Yeah, the derivative is down. Oh, let me just confirm finally. Newton's formula. Newton method formula. Yeah. So I know it is just the F prime, I'm not sure about. Yeah, F prime is down. Yeah, F prime is down. So it was fine the first time. F prime is actually down. Okay. Okay. So F prime is down. So F prime is down here. So that's the Newton method, like that. Okay, so yeah, because this H inverse means that it goes down. So Newton's method uses the approximation, but in matrix form, right? Newton's method uses the approximation theta of k plus 1, theta sub k plus 1 is equal to theta sub k minus H inverse. This is the Hessian matrix now. H inverse grad E. So where H is the Hessian matrix. So for the least square subjective now, E is actually half R transpose R, which we also saw the other time as J transpose R. So the exact Hessian then contains two terms. H is equal to J transpose J, because if we multiply through by the Hessian now, so we have H is J transpose J plus summation from I equals 1 to n of R sub I del squared Ri. That's the gradient squared R of Ri. So the second term involves the second derivative of residuals, as we find here. So computing these second derivatives can be expensive. It can be such a task, right? So the Gauss-Newton, so we have that's the Newton's method right there. So it has second derivative. On the other hand, the Gauss Newton approximation ignores the second order residual term. So in this case now, this term is gone. I will just have J transpose J. So you see, this is more like a simple form, and then we move that to this more complicated form. And that is why the LM algorithm is somewhere in between both of them. So talking about the Gauss-Newton approximation, which ignores the second order residual, the Hessian is approximately J transpose J. Therefore, we then have that the grad of E is actually J transpose R, and the Gauss-Newton step evolves. The Gauss-Newton step solves J transpose J grad equals minus J transpose R. Thus, we say grad along Gn, that's for Gauss-Newton now, is minus J transpose J inverse, right? That is, if we take this over to this place now, so we have minus J transpose J inverse, then J transpose R like that. So that is in the case where the inverse does exist. Now the question is why Gauss-Newton can be dangerous. We need to watch that. So the Gauss-Newton matrix is J transpose J. Although this matrix is positive semi-definite, it can be poorly conditioned or it can be singular. Singular meaning that it has no determinant. It cannot be inverted. The inverse cannot be found. So this creates several problems. Problem one is singular matrices. If the columns of J are linearly independent, then J transpose J may be singular. That is, it is not invertible. It doesn't have a determinant, and then the inverse cannot be found, because for the inverse of a matrix to be found, it has to be it should have a determinant. Then problem two is poor conditioning. Even if J transpose J is technically invertible, it may be numerically unstable, right? So problem three is talking about large steps. So when the curvature approximation is poor, the Gauss-Newton step can become excessively large. So we have problem four too, also, which is far from the optimum. The Gauss-Newton works particularly well when the residuals are already relatively small. It's more like when you do the one for maybe a single function, right? So if you need an initial guess. So for instance, to implement this kind of expression we have here, you need an initial guess. So you need an initial guess x naught. For instance, for the first value x1, you have x naught minus f of x naught all over f prime of x naught. So you need to be able to guess this x naught. X naught can actually be anything because it is just a guess. But if it is close enough to the actual solution, you can get a faster convergence of your steps, right? So if your initial guess, for instance, in this case, we are dealing with matrices, we are dealing with tons of parameters, so it can be, with many parameters, so it can be such a problem. So Gauss-Newton works particularly well when the residuals are already relatively small. So far from a solution, its local quadratic approximation will be unreliable. This motivates the Levenberg-Marquardt modification. So the inefficiencies of the Newton and the Gauss-Newton methods is what has led to the idea of the Levenberg-Marquardt algorithm. So the Levenberg-Marquardt algorithm modifies the Gauss-Newton equation by adding a damping term. So the damping is what makes the difference. So instead of solving J transpose J grad equals minus J transpose R, then Levenberg-Marquardt solves J transpose J plus lambda I. So in addition to J transpose J, now we now have plus lambda I, where lambda now is a damping parameter. Then, of course, multiplied by this. So this is more like the grad now, the gradient. That is equal to minus J transpose R, where lambda, the damping parameter, is always positive. So that is the damping parameter. And then the updated parameters are then theta sub k plus 1 equals theta sub k plus plus grad. So you need to solve grad here and add it to this theta sub k to get theta k plus 1. So the biggest issue is solving this delta here. So the identity matrix I, this identity matrix I prevents the matrix from becoming singular when lambda is sufficiently large. So this helps to balance things out. So now the question is why the damping parameter? Why the damping parameter matters? The damping parameter lambda controls the character of the optimization step. So when you have small lambda, small damping parameter, so for instance, when lambda is approaches zero, when it's very small, like it's close to zero, we obtain approximately J transpose J grad equals minus J transpose R because it's very small, right? So because it's very small, so if you multiply by I, it's as good as you have J transpose J. So very small lambda makes the behavior still look like the Gauss-Newton equation where we're coming from. So on the other, in that case, we have the Levenberg behaving like Gauss-Newton when the damping parameter is very small. So it behaves like Gauss-Newton. On the other hand, when we have large lambda, when lambda is large, then we have J transpose J plus lambda I to be approximately lambda I. Because this is because this is large, it can dominate the J transpose J. So we can then have, so if it's a very large, so we have it dominating, and then this whole expression is approximately lambda I itself. Therefore, we can then have the grad to be approximately minus 1 over lambda J transpose R like that. So because this is close to this, now we just on this side, coming here, we just have yeah, I think this is the one we can use. So because this whole thing is close to this, now we just have grad alone is just lambda I inverse multiplied by this other part. And that is exactly what we have here. So grad, the gradient is equal to minus 1 over lambda J transpose R like this. So since uh, okay, this is grad, and this notation is always confusing for me. So this expression, I think this is del. So del E now is J transpose R on this side. So we can obtain approximately grad to be equal to grad. I think I'm confusing these terms, but just follow the signs. Should I call this triangle and call this grad? So this triangle now is approximately minus 1 over lambda grad E. So this resembles the gradient descent. So you see a switch between gradient descent and the Gauss-Newton method, depending on the largeness or on the size of the damping parameter. Small damping parameter makes behavior similar to Gauss-Newton, while very large lambda damping parameter makes the LM algorithm behave like gradient descent. Thus, LM smoothly connects two optimizing strategies. So, in summary, we have this idea that gradient descent goes to Leven. So, Levenberg-Marquardt is a transition between gradient descent and Gauss-Newton, depending on whatever the parameter looks like. Small parameter, you have the behavior close to Gauss-Newton. Large parameter, you have the behavior close to gradient descent. And the geometric interpretation, suppose the current parameter vector is theta sub k. So a first order approximation gives r into theta sub k plus this is grad, right? Uh I yeah, this let me call this is del. This is del. So r into theta sub k plus del is approximately r into theta k plus j del. So Levenberg-Marquardt chooses del by balancing two objectives. Reduce the linearized residual, one, avoid taking an excessively large parameter step. Okay, so this can be written as a regularized problem. So we have some kind of regularization here. In machine learning, we have regularization problems like setups like ridge, lasso, and of course the elastic regression. So in this case, we are minimizing del for the square of the absolute value of r plus j del plus lambda, then square of the absolute value of del. So the first term, s- the first term asks, how much can the residual error be reduced? So this one, it's asking how much can the residual error be reduced. The second term is asking how large is the parameter update. So that's what is balancing. So these two things are balancing themselves out. So how much can the residual error be reduced here? And then here, how large is the parameter update? So the damping parameter controls the trade-off. So this lambda is controlling the trade-off between, the residual reduction of the residual error, and of course the largeness of the parameter updates, that like that. So talking about the deriving the Levenberg-Marquardt equation, consider Q of del to be half then norm of norm of R plus J del squared plus lambda over 2 norm of del squared. Expand the first. So if we expand this first one now, because we're dealing with matrices, don't forget, we have half into R plus J del transpose multiplied by R plus J del. And on this other hand, we have lambda over 2. Then because this is squared, now we have del transpose del. So differentiate with respect to del. Now, if you differentiate with respect to del, we then have, this is squared there. So grad differentiated with respect to del for Q now, we have J transpose. So because del is here, and if you differentiate del, so this is more like square. So if you differentiate with respect to del, J has to come out. So you have J transpose into R plus J del plus here. If you differentiate with respect to del, so it's more like del square. So 2 cancels 2 here. They just have lambda times del like that. So if you set the derivative equal to 0, so this J transpose R plus J del plus lambda del, we have J transpose R plus J transpose J del plus lambda del equals 0. Therefore, we can have it that J transpose J plus lambda I multiplied by del is equal to minus J transpose R, like this. So we transfer this to the other side. So del itself will now be, so we transfer this. So if we transfer there, we have minus J transpose J plus lambda I inverse multiplied by J transpose R, like that. And then we can, so for each del we get, we can have theta sub k plus 1 to be theta sub k plus del. So do not explicitly compute the matrix inverse. So that's one instruction here, that we don't explicitly compute the matrix inverse. Although the mathematical expression says del is equal to minus J transpose J plus lambda I inverse. So this inverse is key. So, and that multiplied by J transpose R. So we should generally not compute the inverse. This inverse, we don't compute it explicitly in Python. Instead, we solve the linear system. So we rather solve the linear system such that we can just now get the del out of that. So numerically, this is more stable and usually more efficient if we solve the linear system instead of getting the inverse directly. So in Python, what we used to do to make sure that works is we have a delta to be, so this delta, delta is equal to np dot lin from the linear algorithm, linear algebra uh module from the numpy function. Then we have from the numpy library, we have a function called solve. So we use that instead of finding inverse directly like that to get our del. Now, with that in place, we can have an example for a one Levenberg Marquardt step. So suppose J, the Jacobian, is 100 to 11 like that. And R, the residuals are 1 to 1. And then the damping parameter is lambda equals 1. So first we calculate J transpose J. So to calculate J transpose J, it means we transpose J, that's 1002. So we need J transpose J. J is 1002. Then lastly, we have 1 1 like this, 1 1. So to compute J transpose J, we need, this is J transpose J. That means we transpose this. So rows become columns. So row 1 becomes column 1, row 2 becomes column 2, row 3 becomes column 3, and then J itself, we have 1002, 1 1. And what I explained previously, if you follow other playlists where I teach matrices, so this one has 2 rows. As a result of that, our J transpose J is just going to be, we write each of these columns twice. This column, we write it twice. This one, we write it twice. So this is how that goes. We have 101, 101. On the other hand, we have 021, 021, 021, 021. And then we can invert these expressions. Now, this 101 here, we invert it over the top. 101. This is 1, 1. So this is 101. And this other one, 0 to 1, we have 0 to 1, 0 to 1, like this, so that J transpose J now is equal to 1 times 1, 1. So that's 1, plus 0 times 0, 0, 1 times 1, 1 again. Then up here, 0 times 1 is 0, 2 times 0, 0, 1 times 1 is 1. This is 1 times 0, 0, 0 times 2, 0, 1 times 1, 1. This is 0 times 0, 0, 2 times 2, 4, 1 times 1, 1, like this. So that J transpose J is equal to 2, 1, 1, 5, like that. 2, 1, 1, 5. That's what J transpose J looks like. So that's 2, 1, 1, 5. Therefore, we can then have J transpose J. J transpose J for plus lambda I. Lambda is 1. So, and since it's a 2 by 2 matrix, this lambda I will simply be 1, 0, 0, 1. So that'll be 1 plus 2, you have 3. 1 plus 0, you have 1. Then 1 plus 0 again, you have 1. Then 5 plus 1, you have 6. Because lambda I, see lambda I now, lambda I is equal to lambda times 1, 0, 0, 1. So, and since that is 1, so 1 into 1, 0, 0, 1. So this is 1, 0, 0, 1, like this. And then J transpose J plus lambda I is equal to what we had, 2115, 2115 plus 1001, and that is equal to 2 plus 1, 3, 1 plus 0, 0, 1 plus 0, 0, 1, 5 plus 1, 6. That's exact, yeah, sorry. 2 plus 1, 3, 1 plus 0, 1, 1 plus 0, 1, then 5 plus 1, 6, like that. So with that in place, next we can now do J transpose R. J transpose R, so R is 1, 2, 1. So for J transpose R, we then have 2, 5. So again, don't forget J transpose, which we had here. R is 1, 2, 1, right? So, and J transpose is this. So down there, J transpose R is equal to the transpose 1, 0, 0 to 1, 1. 1, 0, 0 to 1, 1, and then 1, 2, 1. So because this is 2 rows now, we have to write this twice. So J transpose R is equal to 1, 2, 1, 1, 2, 1. So, and then we invert each of this. This 1, 0, 1, then the other one 0 to 1. Then we add and multiply and add. That's 1, 0, 1. That's 2. Then 0, 4, 1. That's 5. So J transpose R is 2, 5, like that. Then so for the LM system, then will be J transpose R plus lambda I here. Then we have del 1, del 2. That is equal to minus 2, comma 5. So we then have a system of simultaneous equations now. So we have, so if we expand this now, so that's like delta 1, delta 1, 3, 1. That's 3 delta 1 plus delta 2 equals minus 2. Then 1 times delta 1, that's 1. 6 delta 2 equals minus 5. So if we solve this up, this gives approximately lambda 1 equals minus 0.56, 5652. Then lambda 2 is minus 0.7391. Of course, we can, let me see. Yeah, we can use Desmos to deal with this. If you don't want to solve that explicitly, you can just quickly graph it and get the result. So you just use X and Y here. So first equation is more like, so first equation is like 3x plus y equals minus 2. So you have 3x plus y equals minus 2. So you have that 3x plus y is minus 2. Then you have x plus 6y equals minus 5. X plus 6y equals minus 5. Okay, so the solution is somewhere around here. So where they intersect, that's minus 0.41, minus 0.76. Okay, 1 plus 6y, right? That's x plus 6y is minus 5. X plus 6y is minus 5. The first one, 3x plus y. 3x plus y is minus 2. Yeah, the solution is somewhere around it. Minus 0.41, minus 0.76. So I think there's a bit of It should be minus 0.41. So something is a bit off here. So we can easily correct this. So let me see, 3x plus y is minus 2. Okay, then x plus 6y equals minus 5. So that's minus 0.4118 minus 0.4118. Okay, let me see, x is, yeah, minus 0.4118, right? Minus 0.4118 minus 0.4118. Then the other one is minus 0.7647. 0.7647, like that. So we can then update this now. Minus 0.4118, and this is minus 0.7647, like this. And that's what we have there. So we have this. So the damping parameter, the damping term prevents the update from behaving like an uncontrolled Gauss-Newton step. So the damping parameter helps to the whole system from not behaving like an uncontrolled Gauss-Newton step. Now let's look at a small neural network. So consider a neural network with one input variable, two hidden neurons, one output neuron. So that's like one input, one output, then two hidden neurons. I think we've encountered such things in the past. So for neural network, right, it's more like you have connections ongoing like that. So you have let's say you have the input here. So you have this input, and then there's a way these things are drawn. So these are the hidden layers now in between. Then you have the outputs. So this can be done better for sure. Um, like that. So if you consider a neural network with one input variable, two hidden neurons, and one output neuron, the architecture is 1, 2, 1. So inputs, two hidden neurons, one output. Let the hidden layer use the sigmoid activation. Sigma of z equals 1 over 1 plus e raised by minus z. So for input x now, the hidden neurons will have to be h1 equals sigma of w1x plus b1, and then h2 will have to be sigma of w2x plus b2. Then the output will be y cap. So y cap is v1h1 plus v2h2, whatever we've got here, plus c. So the trainable parameter vector theta will now be w1, w2, b1, b2, v1, v2, c, all of this transpose. So there are therefore 7 trainable parameters in this case now. So w1, w2, b1, b2, v1, v2, and of course the what can be seen as some kind of bias in this situation. Now, talking about derivatives for the neural networks now. So starting with H1, H1 is sigma of W1x plus B1. So H1 W1 will have to be, so differentiate with respect to W1. You have this X out here, right? So you have sigma prime, then the X is out multiplying it. Then partial H1, partial B1. So B1 is constant. So that's going to give 1. So we just have sigma prime of W1x plus B1 because there's nothing attached to B1. Because X was attached to B1, so the X comes out to multiply, that's the expression. Then since y cap now, y cap is v1 h1 plus v2 h2 plus c, then we obtain partial y cap over partial w1 to be, so this is y cap here. So we have partial, so we already know that h is a function of sigma in the first place. So we could actually write this out. So sigma, then partial y cap partial w1 would then be v1, because here now, so the V1 comes out. So we have V1 sigma cap W1x plus V1 multiplied by x. Similarly, we have partial y cap partial B1. That's V1 sigma prime W1x plus B1 differentiating. And if this is confusing, you can substitute the H directly and try to differentiate directly so you get the clear picture. So for the output layer parameters, then we have partial y cap partial V1 equals H1. Partial y cap partial V2 equals H2, and then partial Y cap partial C is 1 because this is just C. So if R then is Y minus Y cap, that's the residual, then we say that partial R partial theta J equals minus partial Y cap partial theta J, and these derivatives form one row of the Levenberg-Marquardt Jacobian. So we'll talk about the Jacobian structure next. So the Jacobian structure for the neural network. So for n training observation and 7 parameters, the Jacobian has dimensions n by 7. So for observation I, we have J sub I equals dri dw1, dri dw2, dri dw1, db1, dri db2, dri dv1, dri dv2, dri dc. So stacking these rows gives J equals J1, J2 up to Jn like that. So we have this in n places depending on whatever n is. Then the Levenberg-Marquardt update then becomes J transpose J plus lambda I del equals minus J transpose R. This is the central equation used to train the neural network. So this is basically the neural network used to train. I mean, this is the central equation, the Levenberg-Marquardt equation used to train the neural network instead of the standard gradient descent that we use in most cases. Then we go ahead to talk about the Levenberg-Marquardt algorithm, training algorithm. So the basic algorithm, step one, initialize the network parameter. So you have an initial guess, or you set an initial value of each of the parameters, because this is because this is bold, right? It tells you have a couple of parameters. So let's say you have 7 parameters. So it means you're going to have the initial value of maybe there's theta 1 up to theta 7. So you're going to have theta 1 not, theta 2 not, theta 3 not, up to theta 7 not, like that. So because that's the starting point. Then the next you calculate the predictions. Y cap is a function of x by the parameters. So this is your input and the initial guess for the parameters. Then step 3, you calculate the residuals where R is equal to Y minus Y cap. So Y is the observed values and Y cap is whatever the predictions you calculate from here. And in step 4, then you construct the Jacobian J equals dr d theta, from here. And then step 5, you construct the damped Hessian approximation where you have the Hessian for the Levenberg-Marquardt, which is J transpose J plus lambda I. We saw how we derived this initially. And then step 6, you solve this now. You solve this for del, just like the setup we have. So H sub LM del equals minus J transpose R. In step 7, you propose new parameters. Theta trial equals theta. So theta trial is equal to the theta you had up to that point plus the del you solved from here. And in step 8, you calculate the new error. If the error decreases, you accept the update and reduce lambda. If the error increases, you reject the update and increase lambda in that case. So step 9, you repeat until you get a convergence. So then we talk about adaptive damping. So the damping parameter does not need to remain constant. So lambda does not have to be a fixed value. It can keep changing to improve the search for an optimal result. So a common strategy is a successful step will be something like if the E of new theta is less than the E of old theta, then we accept the update and decrease the lambda. That is, if the error with the new value is less than the error with the old value, so you have to you accept the update and you decrease your lambda. So lambda lambda over v can now take the place of lambda. So that's some kind of decreasing by a factor where this lambda over nu rather becomes lambda, where lambda is less than 1. So I mean lambda is greater than 1, because if lambda is greater than 1 and you divide lambda by if nu is greater than 1 and you have lambda over nu, it's going to be definitely smaller than the lambda you had before. So this makes the algorithm more Gaussian, more Gauss-Newton-like in that case. Then you can also have an unsuccessful step if the new loss, the new residual, the new difference is greater than or equal to the old one. That means nothing is changing or the prediction is getting worse. So you reject the step and increase lambda. So in this case now, you instead of dividing by nu, you multiply by nu to get a bigger value of lambda. So this makes the algorithm more gradient descent-like in that case. So a simple implementation might use nu equals 10, for instance. Therefore, good step means reduce the lambda, and bad step means increase the lambda. So we can have a Python implementation for that. So we just want to generate an artificial data set, kind of. So import numpy as np, numpy as np, matplotlib as pyplot, because we need to visualize. Then set random seed for reproducibility, because if we don't set this line 6, each time you get different answers because you're going to use random functions here. So let's say we want x to be between -2 and 2, for instance, and we have the actual function we are using, 0.5 x cubed minus x squared plus x. This is what we want to optimize. This is like the loss function, so to speak. So, and we add some noise. So we have 0.5 plus random noise, taking the length of that x, and then the actual y is the true y, which is this, plus the noise we have added now. Okay, so, and then if we try to plot that, if we plot that, we have that right here. So you have the x values, you have the x values here, and you have the y values here. And the observed function and the true function look, they really agree together. So, and from there then, so they seem to agree well. So because of the noise, now they don't align perfectly in some cases, but more or less they are good. The fit is good. So you have nonlinear regression data set here. So this is an artificial data set generated from here, by adding the actual function and then some noise. Then you can then have a sigmoid function. So for the sigmoid function, you import SciPy special. So if you check my playlist on numerical computation with Python, you will see scientific computation, I think, with Python, you will see the special function, the special module under the SciPy library. And here we define the sigmoid function, SciPy the special x bit, which is what gives the sigmoid function, and then the derivative of that, which is s multiplied by 1 minus s. So we can have this also. So no result here, but it's heading forward. That's ahead of what we are going to have next. Now imagine neural network used in the implementation. We use a network with one output, five hidden layers, and one input, five hidden layers, and one output. So the hidden layer contains five sigmoid neurons like that. So it means we are going to have more things to deal with. So the output layer is linear because the problem is a nonlinear regression. So the parameter vector contains five hidden weights, five hidden biases. Then we also have five output weights and one output bias. So altogether, we have 16 parameters. Therefore, P is equal to 16 trainable parameters because we have five hidden weights, five hidden biases, five output weights, and one output bias. So P is 16 for trainable parameters. So in this case, N hidden is 5. Number of parameters will be 3 times number of hidden plus an extra one. Then we have number of parameters printed to be 16 like that. Then we also have parameter initialization. So we can initialize parameters like this. We have initialize the parameters with number of hidden parameters. So you have RNG, random default 42, then W1, W2. So you make sure it follows a normal distribution. It's followed from 0 to 0.5. Same for B1. Then we have B2 also defined this way, and you have B2 to be 0.0. Then you can put everything together, the weights and the biases like that. So that's the parameter initialization we have there. Then we unpack the parameters now. So to unpack parameters, theta and the hidden dimensions, we have W1, theta, everything from beginning to all to the number of hidden parameters. Then B1, everything from theta to from number of hidden parameters to 2 times number of hidden. W2 now, we have 2 times number of hidden times. So it's more like from 0 to number of hidden. Then B1 from number of hidden to 2 times number of hidden. W2 theta, that's from 2 number of hidden to 3 times number of hidden parameters. And B2 is theta minus 1. That's the last value. So, and then we return W1, B1, W2, B2 like this. And this goes. So that is run now. Then we can also have forward propagation. Now, the idea of forward propagation, if you can also check the mathematics of artificial intelligence playlist to understand the whole idea of forward and back propagation. Now, forward propagation is what helps to make one prediction, while back propagation is what helps to correct whatever errors, to improve the error correction, to reduce the loss overall like that. So forward propagation helps us to make one prediction. So you now say, and that's why the function is predict. So you define the function predict that takes in theta x, that's the input, and then the hidden layers, and then you have W1, B1, W2, B2, unpack all the parameters with respect to theta and all the hidden layers. Then you have Z1, So you have X times W1 plus B1 like that. And then H is sigmoid that takes in the Z1. And then Y cap for the prediction is H times W2 plus B2. And you return Y cap like that. So that's for propagation happening there. And for the residual vector, that's Y minus Y hat, the observed value of Y and the predicted, which is we got from here. So we also define the residual vector like that. So we are defining all this function ahead to be used later on. Now, talking about constructing Jacobian. So imagine H sub j is sigma of W sub j x plus B sub j, and Y cap is summation from j equals 1 to m of V sub j, H sub j plus C. So for one observation, you have dy cap over dwj, and then so dy cap over dwj, so you have V sub j. Because here H sub j is inside there, so you could also throw this in here. So it will be easy to see what exactly is happening. So if you put sigma in place of H sub j, so the Y cap dwj, because wj is a function of sigma, so we have vj is out, v sub j is out here, and then we have sigma prime, then the wj, with the wj, you have x out here, so you have v sub j sigma prime w sub j x plus b sub j x. Then we do that for b sub j also. So because b sub j doesn't have anything attached to it, so we just have v sub j sigma prime wj w sub j x plus b sub j, and then we also have dy cap dv sub j. In that case, now that just goes straight. So that just remains h sub j, because this is constant, it goes away. And then we can have dy cap dc. Dy cap dc just gives us 1. And then the residual is r equals y minus y cap. So that way we can set up the Jacobian. All these derivatives receive a negative sign when constructing the residual Jacobian. So, and that we define here in Python. So define the Jacobian, taking theta, the input and the hidden layers. So you have W1, B1, W2, B2, unpack the parameters theta and n hidden, then define your Z1, the sigmoid, the derivatives. Now, see, that's sigmoid derivative of Z1, and then we have n is length of x. I mean, we've already defined sigma derivative up somewhere before. I think this is here where we had to define that s into 1 minus s for sigmoid. I think, yeah, sigma derivative function. So we are calling this function. So everything you are doing after now is still connected with everything we've done before, because we've not really got any results. We've just been setting up the whole system so we can go to where we want to go. So then you can initialize J with the correct number of columns. That's 3 times hidden layers plus 1. That's if you have 5 hidden layers, that's 3 times 5, 16, 15 plus 1, making all trainable parameters 16. So J now is, so you initialize the zeros now. So you have n by 16, whatever n is, n by 3nx, 3n plus 1. Then for the derivative with respect to hidden weights, W1. So you have J from, so you have this, all of it, then you have up to hidden, then minus dh into x. So you define all this. Then derivatives with respect to hidden biases. Hidden biases, you have B1. So same kind of setup. Then derivatives with respect to output weights. So all those things we differentiated before. Here we got minus h. Then derivative with respect to output bias B2. That's the last parameter. We get minus 1.0 like that. So don't forget to run this so that it can work for at the end of the day when you finally run the whole thing. So this is done now. So implementing one Marquardt step. So define LM step, taking theta, x, y, n hidden and damping. So R is residual, so you have theta, x, y, n hidden. J is Jacobian, theta, x, n hidden. So A now is J transpose times J. That's that setup we have. Then the damping, which is lambda times I length theta. That's just this more like some steps. So and then G is J transpose times R, and then delta is now solve the system with A minus G, and then you return delta like that. So that's implementing one LM step. Then you can complete LM training function now. So define train LM. So you have X, Y, hidden layer 5, maximum iteration, take 500. Damping is 1.0. Damping factor is 10.0. Tolerance is, so this damping factor is the new. So in case, so when you try one step and you discover that the prediction is better, it's not changing or it's worse, then you increase the parameter by multiplying by 10. But if you do one step and you discover the prediction is good, so you reduce the damping parameter by dividing by that damping factor 10. So you divide it by 10, and then you have a tolerance. So that tolerance tells us at what point we get to stop. You have theta initialize the parameters with the hidden layers. The history, this is some initialization. So for iteration in the range of the number of maximum iteration, that's from 0 to 500 as has been specified. R9 is residuals, taking theta, x, y, and the hidden. Then error is 0.5, sum of r squared. Then you have the history dot append. So you keep updating the error. Then you have the Jacobian. So you keep solving this. So if the error trial is less than the error, theta is theta trial. Damping is, so you divide damping by the damping factor, then damping down becomes the new damping, then else the damping is multiplied by the damping factor. So this works for when the predictions are getting better, or when the predictions are getting worse, you increase the damping by multiplying by the damping factor, and you keep on the steps like that, and that returns theta and the history that you have like that. So let me run this because it's going to work towards where we're going. Then you can now train the network at this point. So to train the network now, you have theta LM, which you've defined already, history, which is train LM, XY, and all of this. So if you do this now, you discover the final loss is like 0.24, which is small, right? Maybe not too small, but at least small enough. The number of iterations that takes is 477. So it doesn't have to take all the 500 iterations before meeting the criteria. So if you want more accuracy, all you just need to do is the tolerance level. This tolerance, you can increase it to say, if this is now 10 raised per minus 10, 1 e raised per minus 10. So it means so you may need more iterations to go. So you may have to use the whole 500. So if I come back here now, you discover that now 479 iterations are now used, but it doesn't do, the difference is not so serious. Then you can now plot the training loss. So you plot the training loss here. So you use the history now, the history of the values as they are reducing. So it's more like you're descending a hill. And that's the good thing there. So it starts from something above 100, the sum of squared error, and then it keeps going closer and closer to zero as the number of iterations. But I mean, as you get to a point, the reduction slows down. It just keeps going and going like that, approaching zero. So then evaluate the fitted network. So you can evaluate the fitted network by using certain metrics like the root mean squared error, right? So which is what we have here. So yeah, you have 0.1109. Then you can visualize the neural network fit. So that's some plots in there. You plot from -2 to 2, which we started with, and the y plot for the predicted value. So that's the observed data rather. That's y plot. So you have the observed data. So the observed data is all the dots, and then LM is the neural network, what we did with the Levenberg Marquardt neural network. And then the true function, that we started with, that's the orange one. So we put all of that together. So X plots, Y plots, so Y plots is for the neural network because it takes all the theta, LM, X plots, and all that. And then here we have XY, that's the observed data we started with. And then we have the true function also, which we had at some point. So you see all of them looking pretty together. And then checking the Jacobian. So the Jacobian is one of the most important components of the Levenberg-Marquardt. So an implementation error in the Jacobian can cause the algorithm to behave badly. So a useful strategy is to compare the analytical Jacobian with a numerical finite difference approximation. So for parameter theta j, you can have partial r partial theta j, which is approximately r of theta j plus epsilon minus r of theta j minus epsilon over 2 epsilon. So that's some kind of central difference also. This provides an independent numerical check of the analytical derivatives. So if you do that, so you can do numerical Jacobian, with all of this now, and then it returns the value, whatever you have here for the Jacobian. So you can now compare that with compare analytical and numerical Jacobians now. So for the analytical, we got it based on the theta sub LM with the input and number of hidden layers of 5. And for the numeric now, so you're computing that. So numerical Jacobian, which is what we defined up here now, based on all of these things. So the numerical Jacobian, so if you do that, we see that the maximum difference is 2.29 times 10 raised per minus, and that's a lot. That's really small because that'll be like 0.000000000 229, and so on. So a sufficiently small maximum difference indicates that the analytical Jacobian is consistent with the finite difference approximation. This is an important debugging technique when implementing second order optimization algorithm. So this small value tells us that we are doing something, that everything is going well. Then now, why can Levenberg-Marquardt convert faster than gradient descent? Because gradient descent is the what is that thing called? It is the state of the art algorithm for AI systems, for neural networks and all that. So why can Levenberg-Marquardt convert faster than that? So gradient descent uses delta to be minus eta delta grad E, where eta is the learning rate. Therefore, delta is minus eta J transpose R. The update direction depends only on the gradient here. So Levenberg-Marquardt uses delta, which is minus J transpose J plus lambda I inverse J transpose R. Therefore, Levenberg-Marquardt incorporates information about the local curvature through J transpose J. So this allows LM to adjust the magnitude and direction of the parameter updates according to the geometry of the problem. Consequently, LM can converge in far fewer iterations than basic gradient descent for many small nonlinear square problems. So the problems have to be small enough. So gradient descent versus Levenberg-Marquardt. Now, so let's do a proper comparison. So we compare them across certain properties. So uses gradient, yeah, both of them use gradient. Uses Jacobian. Gradient descent does not necessarily need Jacobian, but LM requires Jacobian. Curvature approximation, no for gradient descent, yes for LM. Then main matrix, none for gradient descent, but J transpose J plus lambda I for LM. Memory requirement is relatively low for gradient descent, but it is higher for Levenberg-Marquardt because you have more terms you need to talk about. Then you have step computation. It is cheap with gradient descent, but for Levenberg-Marquardt, that's more expensive. Convergence is often slower with GD and faster with LM. Then large networks, excellent for large networks. Gradient descent is excellent for large networks. Then LM is often impractical for large networks. So you can only use it for small size or medium size neural networks. Then small regression networks. Gradient descent is good for small regression networks and excellent for LM is excellent for small regression networks. So sum of squares objective is not required for gradient descent, but it is required for it is especially LM is especially suitable for that. Then adaptive damping is not necessarily for gradient descent, but it is necessary for Levenberg-Marquardt algorithm. So the central trade-off is this: for Levenberg-Marquardt algorithm, expensive iterations but potentially very fast convergence versus gradient methods, cheap iterations but potentially slower convergence. So we have to decide what exactly you want to achieve. So relationships between LM and backpropagation. So like I said earlier, so in any AI process, there are two things. That you have the forward propagation and the back propagation. The forward propagation is what takes you to your prediction, and the back propagation is what helps you to adjust the error, to keep correcting the error. So it is that back and forth that you keep having until you get you get a value, a loss value that is acceptable. So forward propagation, it predicts a value. So that value, so based on that value, that predicted value is compared with the objective, with the observed value, and then the loss is computed, and then backpropagation helps to adjust the weights and parameters to ensure that, and when the next prediction is made, the value is the loss is smaller, and that process goes. So forward propagation is for prediction, while backpropagation is for learning, what you can call learning when you hear things like machine learning or statistical learning. So backpropagation is for learning. So once the learning is done, another prediction is made, and it goes back and forth until the right result is attained. That is, we achieve a loss that is small enough to be accepted. So backpropagation and Levenberg-Marquardt are not competing concepts in exactly the same sense. So backpropagation is primarily a method for efficiently computing derivatives. For example, backpropagation can calculate the y cap, the theta j for every network parameter. While the LM then uses these derivatives to construct the Jacobian, and then the optimization step is subsequently obtained from J transpose J plus lambda I delta equals minus J transpose R. Therefore, a neural network can conceptually use forward propagation to back propagation to Jacobian to LM update. Then when the LM update is obtained, forward propagation goes again, back propagation, and it keeps going until we get the good result. So in practical implementations, automatic differentiation can also be used to construct the Jacobian. Well, I mean, in deep learning, like when you use things like PyTorch, so these libraries are designed to do tons of computation efficiently. So we have Levenberg-Marquardt as an approximate second order method. So the exact Hessian of E equals half R transpose R is actually H, which is J transpose J, plus summation over I of Ri grad squared R sub I. So, and the Gaussian Newton Gauss Newton approximate this as H, which is approximately J transpose J. Then Levenberg-Marquardt then modifies the approximation HLM to be J transpose J plus lambda I. Thus, LM can be viewed as damped Gauss Newton method. So because only this damping is what is added to it. So this gives it a second order flavor without requiring the complete exact Hessian. Then we talk about trust region interpretation. LM can also be interpreted as a trust region method. Instead of allowing an arbitrarily large update, we restrict the step, we restrict the step to be less than or equal to the absolute value of the delta is less than or equal to delta. So the algorithm asks, how far should we trust the local linear approximation of the residual? Then if the local approximation works well, the algorithm can take more aggressive steps. So if it performs poorly, the algorithm becomes more conservative. The damping parameter lambda acts as a mechanism for controlling this behavior. This interpretation explains why Levenberg-Marquardt is often robust in nonlinear least squares problems. And then we have understanding the damping parameter. Consider three regimes. Regime 1, very large damping. So you have lambda is greater than or equal to the absolute value, the norm of J transpose J. Then del is approximately minus 1 over lambda J transpose R. The algorithm behaves approximately like gradient descent in that case when we have very large damping like we saw before. Then regime 2, if you have moderate damping, so both terms will matter in the case of moderate damping. If the value of lambda is moderate, then the two terms will matter. So the algorithm balances gradients. So we have gradient information balanced with curvature. So curvature information plus gradient information. On the other hand, we have very small damping. So when lambda is very small, it means that so this term can as well disappear. So for very small damping, so this term can go. So then we can say del is approximately minus J transpose J inverse J transpose R because lambda I is as good as 0. Then the algorithm behaves approximately like Gauss Newton. Therefore, lambda controls the optimization regime. So we have the major limitation of Levenberg-Marquardt algorithm now. Suppose the network has P parameters. The matrix J transpose J has dimensions P by P. Therefore, the computational and memory cost grows rapidly as the number of parameters increases. For example, if P is 10,000, then J transpose J contains 10,000 raised power 2, which is 100 million, and that's a lot. So entries, so that's 100 million entries, right? So that is already a very large matrix. For modern deep neural networks with millions of billions of parameters, conventional Levenberg-Marquardt is therefore generally impractical. This is why large neural networks are normally trained using methods such as SGD, Momentum, Adam W, other stochastic first order or specialized second order methods like that. So this is stochastic gradient descent, momentum, Adam, and all of that. Then LM is naturally a batch optimization method. So the Jacobian is constructed from the training observations J, which is a subset which belongs to R, an n by p dimensional real number system. Therefore, Levenberg-Marquardt traditionally uses many or all training observations to calculate the updates. This differs from stochastic gradient descent, where an update may be computed from a small mini batch. So LM is consequently most attractive when the data set is relatively small, the network has relatively few parameters, high quality convergence is important, and the objective is a non-linear least squares problem. Those are the conditions. So using LM for regression now, LM is particularly natural for regression. So suppose y sub I is f of x sub I, comma theta plus epsilon I. The residual is then Ri equals yi minus f of x sub I, comma theta. So the objective becomes E of theta. That's the loss now. That's 1 over 2 summation for over I of yi minus f of f of x sub I, semicolon theta all squared. So this is exactly the non-linear least square structure for which LM was designed. So applications include function approximation, curve fitting, parameter estimation, system identification, scientific modeling, engineering calibration, and small neural network regression. So what about classification now? Now, LM can be LM can be used with neural networks for classification, but the situation is less natural. So it is not natural for classification problems like that. So for binary classification, a neural network may produce P sub I, which is sigma of Z sub I, and the standard loss is binary cross entropy. L equals minus summation all over I of yi log pi plus 1 minus yi log 1 minus pi. So this is not directly a standard nonlinear least squares objective. So LM is therefore most naturally suited to squared error objectives, not binary classification. So one can formulate classification as a least squares problem, but this may not be statistically or computationally preferable to methods designed for cross entropy optimization. So the question is, why does damping help? Why damping helps? Suppose the Gauss network matrix we have is J transpose J, which is 1,999,999,998. The matrix is nearly singular because it's almost like all the values. So when you do the determinants, it's very close to zero. And in that case, we say the matrix is singular. So attempting to solve J transpose J delta is equals minus J transpose R may produce a numerically unstable object. Now, if you introduce lambda to be equal to 10, which is the damping parameter, then we have J transpose J plus lambda I. So that would automatically just add, so it will add 10 to the values on the principal diagonal. So 1,000 times plus 10, you have 1,010. 998 plus 10, you have 1,008. While this ones remain. So the diagonal is increased, improving the condition of the system. The damping term therefore acts as a stabilizer. So this is one of the most important practical reasons for using the Levenberg-Marquardt algorithm instead of pure Gauss-Newton. Now talking about convergence criteria now. So several stopping criteria can be used. So you have small parameter updates. So you stop if the delta is less than the absolute value of delta is less than the epsilon, that's your tolerance limit, then small reduction in loss. So you may also decide to stop if the difference between the previous loss and now is less than the particular epsilon you have, or small gradient. So you can stop if the norm of the gradient is actually less than epsilon. That's norm of J transpose R. The absolute value of J transpose R is less than epsilon. Then you can have maximum number of iterations. So if none of this is met, you can just say, okay, after 500 iterations, just stop. Whether it has converged or not, we don't care. Just do 500 iterations and stop. Then maximum number. So stop after a specified number of iterations. A robust implementation typically uses several criteria simultaneously. So imagine a full situation here now. Improved Levenberg-Marquardt training function. Now you define train LM robust. So you have a robust one. So you have the X, Y, hidden 5, maximum iteration 500, damping 1.0, damping factor 10.0, tolerance gradient 10 raised per minus 8, tolerance steps 10 raised per minus 8 still, then tolerance loss 10 raised per minus 10. Then you have your theta, which you initialize with initialized parameters for the hidden layers. Then you have the history, which is to take in values of the as the loss is going down. Then damping history. So for iteration in range this. So and then you have the residuals, the Jacobian, you have the gradient. So like the kind of things we did before, except that now we are making it more robust. So with the whole damping thing, so we run this for the improved Levenberg-Marquardt training function, and then we visualize the damping parameter. So for the damping parameter, and I want to see how the damping parameter is moving. So loss, of course, is loss goes sharply first and then it slows down. Then for damping parameter, see what the behavior looks like. So this is the adaptive damping parameter. So it means once you start with a damping parameter of 10, it doesn't stay there. So it stays at 10 and then it keeps reducing over the iteration. So it keeps changing values depending on what the situation is. So we know that the damping parameter is increased when a good prediction is made, and when a bad prediction is made, it is decreased. It is decreased with a good prediction. With a bad prediction, it is increased, and that is why you can have some ups and downs in the damping process. That is why we have adaptive damping parameter behaving like that. So the complete Levenberg-Marquardt algorithm from everything we've been saying so far is this now. Given iteration initial parameters theta of 0 and damping lambda of 0. So for k equals 0, 1, 2, calculate the residuals. That's the difference between observed values and the predicted values. Then calculate the Jacobian. That's J sub k, which is dr d theta over all the theta k's you have. Then solve the damped normal equations. So you solve this equation now for delta k. Then you construct a trial point. So the theta trial is theta k plus delta k that you got from here. Then you evaluate the trial loss. So it's more like standard procedure in all of artificial intelligence procedures. So each trial equals half the square of the norm of R of theta trial, then you accept or reject. So how do you accept or reject? If the trial value you have is less than the EK, then you accept, and then you have theta k, theta sub k plus 1 is equal to theta trial in that case, and then you decrease lambda. Otherwise, if the reverse is the case, if E trial is greater than EK, then you do the opposite. Then at the end of the day, you stop if convergence occurs. Like if you meet the criteria for tolerance, then you can stop. Then the big picture overall is that the mathematical chain behind linear Levenberg-Marquardt neural network training is simply this now. Uh, you have neural network, you have the predictions. From the predictions, you get the residuals by taking the difference between the prediction and observed values. Then you take the Jacobian of the residuals, then you compute J transpose J, you get the damped linear system, and then you update the parameter and you go over again. More explicitly, you have the residual to be observed minus predicted values. Then J is dr d theta. Then J transpose R provides gradient information, while J transpose J provides approximate curvature information. And finally, you have J transpose J plus lambda I delta equals minus J transpose R, which determines the parameter update. And then we have some important insights. So insight one, Levenberg-Marquardt is fundamentally a nonlinear least squares optimization method. So nonlinear least squares. Insight two, the Jacobian is central to the algorithm. Insight three, the matrix J transpose J acts as an approximation to the Hessian matrix. Insight four, you have this that the damping parameter stabilizes the optimization. Then inside five, large lambda makes Levenberg-Marquardt behave more like gradient descent. Small lambda makes Levenberg-Marquardt behave more like Gauss-Newton. Then LM can convert extremely rapidly for small nonlinear regression networks. Then inside eight, computational costs grows rapidly with the number of network parameters because we are taking J transpose J, so it's like easily squared. Then LM is therefore much more attractive for small and medium-sized networks than for modern deep neural networks. So LM is not advisable for modern deep neural network that contains tons of parameters. Then backpropagation can be used to efficiently compute the derivatives required to construct the Jacobian. So LM compared with major neural network optimizers now. So you have gradient descent, uh, main information used is the gradient. It is very simple and it can be slow, and that's what is used the most in many AI processes. So you have this stochastic gradient descent. So it is a mini batch gradient. It scales well and it has noisy updates. Momentum, you have gradient plus velocity. Information that as information used, then the typical strength is faster optimization, and main limitation is that it requires hyperparameter tuning. Adam is uses adaptive first order information, and the typical strength is that it is excellent general purpose optimizer, and it's not a true second order method like LM. Then Gauss-Newton, the information uses the Jacobian curvature. The typical strength is fast. It is fast near solution, and main limitation, it can be unstable. So if you use Gauss-Newton in reality, right, because of the derivative part, you get to convert very fast. Then for oh, okay, that's not Newton, and that's Gauss-Newton. For Levenberg-Marquardt, you have Jacobian plus damping that we saw. So fast and stable for least squares and expensive for large networks. Newton requires exact Hessian, and the strength is it has strong local convergence. Yeah, this was what I was referring to, that idea of xn plus 1 equals xn plus f of x over f prime of x, and it's a very expensive Hessian is required. That's the limitation because you need that derivative. So when should you use Levenberg-Marquardt? LM is a strong candidate, right? LM is a strong candidate when the network is relatively small. The problem is regression. The objective is a sum of squared errors. The data set fits comfortably into memory. Fast convergence is important. Accurate parameter estimation is more important than massive scalability. All right. So you have to make sure that whatever you're using this for, it fits into all this. So LM is particularly attractive in scientific and engineering applications where the neural network may have only tens or hundreds or perhaps thousands of parameters. Examples include scientific curve fitting, biomedical modeling, system identification, engineering calibration, small nonlinear regression networks, parameter estimation, and function approximation. Then when should you avoid Levenberg-Marquardt algorithm? LM is generally a poor choice when the neural network contains millions of parameters. The dataset is extremely large. Training must be highly stochastic. Mini batch training is essential. GPU scalability is a major requirement. The objective is naturally cross-entropy rather than least squares. For large deep learning systems, methods such as Adam W, SGD with momentum, and specialized large-scale second order or quasi second order methods are usually more appropriate. In summary, a neural network produces predictions y cap, which is a function of inputs and the parameters. Then you define the residual vector r, which is the difference between observed minus predicted. The objective value is then the error, which is 1 over 2 r transpose r. Then you get the Jacobian of the residual, that's partial r partial theta. Then the gradient, you get that to be the grad of the error, and that is J transpose r. Then the Gauss-Newton Hessian approximation is HGN, which is J transpose J. So Levenberg-Marquardt modifies this approximation as J transpose J plus lambda I adding a damping parameter, and then the update is obtained from solving for delta here, and the parameters become theta n equals theta O plus the delta you get. So the damping parameter determines whether the method behaves more like gradient descent or Gauss-Newton. Therefore, the central idea of the entire algorithm can be summarized as use curvature information when it is reliable, but add damping when greater stability is needed, basically. So use only curvature information when it is reliable, but when it is not reliable, use damping like that. So that's basically, and that's the switching you have between Gauss-Newton and Newton methods. So the key takeaways now, the Levenberg-Marquardt algorithm provides a powerful bridge between first order and second order optimization. So for neural network regression, it replaces the simple gradient descent update, theta n equals theta minus eta grad E, with the curvature aware update, theta n equals theta minus J transpose J plus lambda I inverse J transpose R. So the method gains much of the speed of Gauss-Newton while retaining the stabilizing behavior of gradient descent. So you combine the strength of Gauss-Newton and gradient descent together. So its greatest strength is rapid convergence for small nonlinear least squares neural networks. Its greatest weakness is computational cost because the matrix J transpose J grows with the square of the number of trainable parameters. So thus, LM occupies an important position in the history and theory of neural network optimization. So you have gradient descent leading to Levenberg-Marquardt and Levenberg-Marquardt leading back to gradient descent, depending on the damping parameter. Levenberg-Marquardt can lead to Gauss-Newton or Gauss-Newton can lead back to Levenberg-Marquardt, depending on the damping parameter. So using Levenberg-Marquardt also provides an important conceptual bridge from classical numerical optimization to modern neural network training. So again, we have our practice problems. I think, of course, this has taken a lot of time, but I think I should still take solve some problems. Let me see how much we can do. So I'm probably going to take problems 5 and 12. So here you can see problems 1 to 4 clearly. All of problem 1 to 4 here. So, and then you have problem 5, I'm taking problem 5. Using the matrices in problem 4, so these matrices here, we are going to use them in problem 4 to calculate one LM update for lambda equals to, so damping parameter is lambda is 2 by solving this now. So we'll do that. Then so you can see problems 6 to 9, clearly here, 6 to 9, all of that, 6 to 9. Then you can see 10 to 15 here. So the second problem I'll be solving is problem 12. Consider a neural network with one input, 3 sigmoid hidden neurons, and 1 linear output. Determine the total number of trainable parameters, including all hidden layer weights, hidden biases, output weights, and the output bias. So I think the key thing is 1 input, 3 hidden layers, and 1 linear, 1 output. So it has 1, 3, 1. So that's the key information we need from that. So you can see the rest up to 15. Then 16 to 20 now. So let's go ahead and deal with these problems as fast as we can, and then we can bring this to a close. So we have problem 5. Problem 5. So for problem 5 now, we have J is 1, 2, 2, 1, 1, 1, and then R, the residual is 2 minus 1, 3. Then we have lambda to be 2. The damping parameter is 2. So with that in place now, we can say that we know that the Levenberg-Marquardt updates Marquardt update satisfies J transpose J plus 2I, being that's our damping parameter, then delta equals minus J transpose R. Minus J transpose R. So with that in place, then we can have J transpose J. So for J transpose J now, we have 1, 2, 2, 1, 1, 1. So the transpose 1, 2, 2, 1, 1, 1. Transpose means rows become columns and columns become rows. So 1, 2, 2, 1, 1, 1. Then against 1, 2, 2, 1, 1, 1. And that's easy. J transpose J is simply, because this one is in two rows now, we write this twice. So we have 1, 2, 1, 1, 2, 1, then 2, 1, 1, 2, 1, 1, like this. And then we invert this over it. So we have 1, 2, 1 coming here, 1, 2, 1, 1, 2, 1. Then the second one, 2, 1, 1. So that's 2, 1, 1, 2, 1, 1. So that J transpose J now, J transpose J can then be 1 times 1. That's 1 plus 4 plus 1. Here 2 plus 2 plus 1. Here 2 plus 2 plus 1. Here 2 plus. So here now is 4 plus 1 plus 1. So that J transpose J is equal to 6, 5, 5, 6. 6, 5, 5, 6. So that's J transpose J. With that out of the way, we then have J transpose R, which is the next thing we need. Don't forget the equation we are following, this. So we have got this. Of course, this is the unit matrix yeah, this is the unit matrix. J transpose J is 2 by 2, by the way. So this is going to be a 2 by 2 unit matrix. Then delta is what we are solving. Then J transpose R. So for J transpose R, right, we have J transpose again. That's 1, 2, 2, 1, 1, 1. And then R is 2 minus 1, 3. So we have two rows here and one column. So we're going to write this twice so that J transpose R is equal to 2 minus 1, 3, right? That's 2 minus 1, 3, 2 minus 1, 3. So this now gets to become 1, 2, 1. That's 1, 2, 1. And this is 2, 1, 1. So this is equal to 2 minus 2 plus 3, right? 2 minus 2, 3. Then 4 minus 1 plus 3. So J transpose R then is J transpose R is equal to 3, and this is 6. That is 3, 6. We have J transpose R like that. So, and then we have so we can then say J transpose J plus 2I. So we have just that's 6, 5, 5, 6 into 2I. So 2 times the unit matrix, that's 2, 0, 0, 2. And that means we have 8, 5, 5, 8. Like that. That's J transpose J. So the LM system, the Marquardt system, Marquardt system becomes 8, 5, 8, 5, 5, 8 into delta 1, delta 2 equals minus 3, minus 6. So in that case now, we can solve this. So because this is two rows and this is, so we have to write this twice. So that means we have delta 1, delta 2, then delta 1, delta 2, and we invert this over it. That's 8, 5. Okay, no, we write it twice down here. So this is delta 1, delta 2, delta 1, delta 2. So that is 8, 5. So put this over it, then 5, 8, 5, 8, and all of that is equal to minus 3, minus 6, minus 3, minus 6. So that means we have 8 lambda 1, 8 delta 1 plus 5 delta 2 is equal to minus 3. And then we have 5 delta 1 plus 8 delta 2 is equal to minus 6. So we can easily solve this to get the whatever the results are. So let's do this. 8558 minus 3 minus 6. 8558. So now that's 8 5 minus 3 5 8 as 5x plus 8 minus 3 minus 6. So we have a solution somewhere around here. That's minus 8x plus 5y, right? 8x plus 5y minus 3. 5x plus 8y is minus 6. So let's see if we can do fractions now. I think there was a way we could do fractions with this. Is there something with labels we can? That's labels now. Okay, we can even add that there. That's 0.15. Yeah, 0.1538. Then minus 0.84615. 0.1539 in short. Okay, let me just do it like this. 0.15 minus 0.85. Yeah? 0.15 minus 0.85. So we have lambda 1 is 0.15. Then lambda 2 is minus 0.85. Is that what we have? Yeah, 0.15 minus 0.85. Yeah, we can have it that way. So that's what we get. So at the end of the day, we can then conclude that the new parameter vector, the new parameter vector is, so of course, this simply implies that we have delta to be equal to 0.15 minus 0.05 minus 0.85, like this. So the new parameter vector is theta new equals theta old plus 0.15 minus 0.85, like that. So in this case, the damping term 2i, so we can say, so the damping term 2i, makes the system more stable than the undamped Gauss-Newton system. Okay. I think because of time, I want to let me see if I can just the other problem 12. Okay, let me see if I can just take sketches of problem 12. So for problem 12 now, problem 12. So I'll just breeze through that. I won't dwell too much on it. So consider a neural network with one input. So input is 1. So that's one input, right? Then hidden neurons. We have 3 sigmoid hidden neurons. Then we have outputs. We have 1 linear output, basically. And with that in place, so we know each neuron receives the single input. So there's 1 weight per hidden neuron. So each hidden neuron receives the single input, So there is one weight. There's one weight per hidden neuron, hidden neuron. So the hidden layer contains three weights. So we have three weights for the hidden layer. The hidden layer contains three weights. That's one step there. Then again, each hidden neuron also has one bias, giving we now have three hidden biases. Three hidden biases. That's another one. Then next, the output neuron, the output neuron, the output neuron receives the three hidden neuron outputs. Three hidden neuron outputs. So it requires three output weights. Again, we have that. Finally, the total number of trainable parameters is, so we add up the hidden layer, three weights from the hidden layer. So that's three weights from the hidden layer first, then three hidden biases. Then we have three output weights plus one output bias. So all of that will be equal to 10. So we say thus, we have 10 trainable parameters in that case. And what that means, so we have P equals 10. So thus, P equals 10 trainable parameters like that. So if there are n training observations, the Jacobian used by the Levenberg-Marquardt algorithm will have dimensions. Okay, let me see if I can write that. If there are n training observations, the Jacobian used by the LM algorithm will have dimensions n by 10. Consequently, J transpose J will be 10 by 10. In that case, J transpose J will be 10 by 10, will be a 10 by 10 matrix, So this illustrates important feature of Levenberg-Marquardt's algorithm. The computational burden is determined strongly by the number of trainable parameters because the algorithm must construct and solve a parameter space system involving J transpose J plus lambda I. Yeah, so with this, we come to the end of this very lengthy video, but I think it is worth it. You know, so again, I'm just going to flash the questions So try your hands on them and see if you really understand the gist. So here you have 1 to 5. I have questions 1 to 5. I treated 5 already in what I solved. Then you have 6 to 9 here. 6 to 9. Then 10 to 15 here. Then the rest. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, this is a good time to subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges which you'll find out as a click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.